Uh, this idea should be considered as the Haag-Kastler theory for charge fields of the chiral CFT. And the main motivation behind there are several reasons behind this idea, this concept, but the main reason, the biggest motivation behind that is to relate the tensor categories for the VOA representations and the conformal net representations. And the reason that categorical extension can do this task is because it could relate the charge fields, both the charge fields on the VOA side and the charge field and the conformal sets. It could describe the properties of charge fields in a uniform way, which apply both to the VOA picture and the conformal net picture. And so it describes it in such a way that these kind of properties of charge fields captures the data of the modular tensor categories. So this idea is actually motivated by the famous paper of Anthony Wasserman in 1998. In that paper, he computed the fusion rules for loop group SUN. The way he did do that is to use the Braid relations actually for the charge fields of the loop group SUN. And actually it is not just the Braid relations. There is some adjoint. There's an adjoint thing. It is a mixture of the adjoint and the Braid relation. It is what I will call it the adjoint Braid relation. But we will say a little bit more about this point later. Yes, this is the main motivation for the category extensions. So I want to, before I give you some idea of what are category extensions, before I turn to some details, I want to give a quick review of, I want to let you know what, roughly speaking, what are the charge fields. And also I want to first review the kind of relations between the conformal nets and the field operators, the chiral fields. So I want to review the picture of relating the two. I want to review the relation, the very well-known and very classic relations between two pictures of quantum field theory, and especially for conformal field theory. We know that in QFT there are several ways to understand it. We can understand it using the Wightman picture. So in this picture, we have some field operators. These are some operator value distributions. And on the other side, we had a Haag-Kastler picture. These are some net of operator algebras. And if you restrict to the chiral CFT, then this kind of relation was first systematically. So for some examples, it was known for a long time, but for a systematic study for relating the two pictures to the chiral CFT is done in 2018 by Karpi, Haag-Kastler, Longo, and Weiner. And the idea is like this. So in the Wightman picture, we have the theory of vertex operator algebras. So roughly speaking, if you're given a VOA, then you have some field operators defined over the complex variable z, and so these are some holomorphic fields which could take the series expansion. And on the other side, you have the conformal net. So for each open interval I, you have a fundamental algebra, and these fundamental algebras are acting on the same Hilbert space. And these two pictures are related by, but there are several ways to relate it, but in the CKLW picture, we take the smear fields. That is, you choose any you choose any field operator at phi, and you choose any function, smooth function f, which is supported inside I, and you take the average, and then you get the smeared operator. This smeared operator is preclosed, is closable, or at least it is expected that this is always closable. And then you can take a closure, and you can take the fundamental algebra to be the one generated by all these phi of f, where you phi are all the possible field operators and f are all the smooth functions which are supported inside I. Okay, so this is the quick review of how these two are related. And in this picture, on the in the Wightman kind of approach, we have the locality, and on the conformal net approach, we also have a locality. So on the left hand side, the locality is like this. So suppose that I and J are disjoint. I think here there should be some picture here. Uh, so this is I and this is J. So if I and J are disjoint, and f is the function f is supported inside I, G is supported inside J, and if you choose two field operators phi and psi, then the smeared operator phi of f is it commutes with the smeared operator psi of G. Okay, this is the locality in the Wightman picture, but also there is one important thing is that we do not only have this kind of commutativity result. There is a kind of adjoint commutativity because because it is a unitary theory, so we can take the adjoint. The adjoint of a smeared field is also could be also given by so if you take the adjoint, you can find another field which is the adjoint field smeared with the complex conjugate of f. So this is the complex conjugate. So this implies that the adjoint of phi of f also commutes with psi of G if f is supported inside I and G is supported inside J. Okay, so this is the adjoint commutativity of field operators. So this point, the point that we have not only the commutativity, the locality, but the adjoint commutativity is a very important point, which will play an important role in my future discussion of the category extensions. In fact, in category extensions, the adjoint commutativity is apparent, is more explicitly mentioned. And like this, it is implicitly contained in the formula here. For category extensions, adjoint commutativity should be explicitly mentioned. Okay, so this is one thing. This is the locality on the Wightman side, and on the Haag-Kastler side, you just need the commutativity of von Neumann algebras. The von Neumann algebra associated to I commutes with the von Neumann algebras associated with J. Another way to say it is that okay, if you choose phi of f and psi of G, uh, like this, then the von Neumann algebra generated by this commutes with the von Neumann algebra generated by this. By the von Neumann algebra generated by this, it means that it is the von Neumann algebra generated by you take the polar decomposition, which you give a partial isometry and an unbounded operator. And this von Neumann algebra is generated by that partial isometry and the spectral projections of the self-adjoint part. So this is also an adjoint commutativity because phi of f star is also affiliated to the von Neumann algebra here. So this is also not only a commutativity property, but a adjoint commutativity property. Okay, so this is the locality for the conformal net. Okay, so after I review quickly the relations between the Wightman picture and the Haag-Kastler picture, I want to say a little bit about what are the charge fields. So the theory of charge fields are well established both on the VOA side and on the conformal net side. Well, actually, yeah, at least on the VOA side, it is well established. On the conformal net side, it depends on which theory you choose. So on the VOA side, the charge fields are called intertwining operators or called conformal blocks. So there are several names corresponding to the same thing. And roughly speaking, a charge field is mapping between different representations of the chiral fields. So you think about the VOA as a algebraic structure of the chiral fields. So this algebraic structure could act on different representations. You can think about the representation theory of the VOA of the algebra of chiral fields. So so each chiral field preserve the representation. Each chiral field should preserve each WI, but charge fields, it goes between different representations. It will go from one representation to another representation. Okay, so this is one feature of the charge fields. I'm not trying to give you the rigorous definition of charge fields. So this is certainly not a rigorous definition, but this is I'll try to give you some rough ideas of how the chart fields look like. So this is one feature of the chart fields, that it does not stay at one representation. It will go between different representations. This is one feature. Another feature is that it is multi-valued with respect to the complex variable z. So this is the one another important difference between chart fields and the chiral fields. So for example, if you choose wi and wj to be irreducible representations, then you can write phi of z. You can take the series expansion in this way, where the powers of z will contain it might contain some non-integers. So the power could be non-integers. In general, it should be for rational theory. This is a rational number, but anyway, the important thing is that the power would be not an integer. So this means that this expression is multi-valued with respect to z. It means that this expression depends not only on the complex number z, but also on the branch you choose. It also depends on the argument you choose. Okay, so we will see that the corresponding description in the category extensions. So in the category extensions, when we use the Haag-Kastler framework to describe the chart fields, this kind of multi-valuedness will also appear. It is also important to consider the multi-valuedness. As we will see, we should consider not only the intervals I and j, but we need to consider the branch of the intervals inside the universal cover of the unit circle. Or alternatively, we need to consider the argument of the intervals, but not just the interval themselves. Okay. So this is some of the backgrounds for the category extensions. Okay, yeah. Okay, so next, after giving this introduction part, I will try to motivate the definition of category extensions. I will not show you the full definition because the category extension, just like conformance, is defined using a list of axioms. I'm not going to mention all the axioms, but I will mention the two most important axioms. The first one is the locality. I will show you how to formulate the locality axiom for category extensions, how to describe the locality for the Haag-Kastler theory of the chart fields. I'm going to motivate that definition, that piece of axiom using the confusion, because confusion is one major method of constructing categorical extensions. So I will show you how to start from the confusion and get the locality for the Haag-Kastler chart fields for the category extensions. Okay, so what I will do in the following for the next few pages is to review some of the basics of confusion. So if you know confusion, then what I'm saying in the following will sound familiar to you. But I will try to express it in the language which is convenient for my purpose, for the purpose of my talk. So to get confusion, we have to consider representations of the conformal net. So first of all, the conformal net A is acting on the vacuum representation. We call the vacuum representation to be H0. And especially you have a vacuum vector inside H0. And I let Hi, Hj, Hk, and so on to denote representations of A. And if you have an interval I, you can take the interior of the complement to be I prime. I think this is the very common notation in the literature of the conformal net. And you can consider any representation of conformal net, say Hi, as a bimodule, where on the left, the von Neumann algebra associated A to I is acting from the left, and the opposite of the von Neumann algebra of Ai prime is acting on the right of Hi. So in this way, you can think of each representation of conformal net as a bimodule. Okay, and To define the confusion, we have to use some bounded operators from H0, the vacuum representation, to Hi. And these bounded operators should commute with the fundamental commute, which intertwines the action of the fundamental algebra associated to I prime. So we have to consider this the home intertwining AI prime from H0 to Hi. Right, which page is this? This should be page 4. Okay, and so corresponding to these bounded operators, we consider each small I, big I to be to be the set of the subspace of these kind of homomorphisms acting on the vacuum. So in other words, these are the vectors which are created from the vacuum by all these bounded operators. By all these bounded operators. It's paused. Oh yes, can you see it now? I think that it's stopped for some reason. I don't know, but can you see it now?
I can see it, yeah.
But I cannot use the notation. I cannot. It's weird. I cannot use the notation. I cannot use the annotation. It's weird. Oh, anyway, let me just move on. Yes. So these are the vectors which are created from the vacuum by these operators, and we call these vectors to be I-bounded vectors. To simplify my future discussions, I will call these vectors to be I-bounded vectors, and so if you have a Cassie vector here, and then it is created by some bounded operator, which I write it as Z of Cassie and I. Okay, so Z of Cassie and I is the operator inside here, and it creates from the vacuum the vector Cassie. Okay, so there are two important things here. Is that first of all, I-bounded vectors are dense inside Hi, because this is actually a very well-known fact in the confusion theory. And another important feature is the state field correspondence, that is Cassie and Z of Cassie I are this is a one-to-one correspondence between Cassie and Z Cassie I. Okay, so this should be regarded as a kind of state field correspondence. Okay. Still, one more thing before, maybe several more things before I record the definition of confusion is that suppose you have two I-bounded vectors Cassie1 and Cassie2, then you can let Z of Cassie1 I going from H0 to Hi of I, and you can let the adjoint of Z Cassie2I go from Hii to H0. So the composition, which is this, goes from H0 to H0, and it intertwines the actions of Ai prime. So by Haag duality, it should be inside Ai. So this operator is acting on any representation, and it is an element inside Ai. Okay. So, so here is what we should do. Okay, we want to record the definition of confusion. The confusion, let me write this to be Hii fusion Hj. It is defined to be the Hilbert space generated by all the vectors Cassie box times the Cassie fusion I, where Cassie are all the I-bounded vectors and eta are all the vectors inside Hj.
Ben, I think the screen is frozen.
What is? Oh, it's frozen. Oh,
Yeah.
Let me first stop share it.
Yeah.
Let me share this again. Okay, is it still frozen?
It's coming back slowly.
inside. Oh. So it's weird. It's, what about now? Can you,
yeah.
can you see the movement of the slides?
I can see it moving. So
okay, okay. So let me, it's so far so good. So let me know if you cannot see the movement of the slides. Okay. Yeah, so yes, you have some z of Kasi I1 going from H0 to here. You have z Kasi Kasi2I going to here. And then you can take the composition, it acts on any representation Hj, and you can use this kind of gadget to define the confusion. First of all, as a Hilbert space, it is generated by all the Kasi fusion eta, where eta is any vector inside Hj, but Kasi is any I-bounded vectors inside Hi. And it is defined using the very famous formula of inner product introduced by Alan Combe. It is using this expression. You let z. So recall that we have mentioned this is acting on the representation Hj as an element of AI. So you let this acting on eta 1 and evaluate with eta 2. You get this inner product formula. Okay, and then yes, so this is the confusion as a Hilbert space, and I want to let so for some good reasons we want to let z of Kasi I, we regard z Kasi I to be a operator which is actually a bounded operator, which is going from Hj to Hii fusion Hj. It is defined by sending eta to Kasi fusion eta. So this is, so it means that this operator is the left action of Kasi on the Hilbert space Hj. Okay, so in this way, z Kasi I is going from each Hj to Hii fusion Hj. And I sometimes will also switch the order. I will write Hj to the left and the Hii to the right. And the definition of this is just the same thing here. So these two, I will always freely change the order. So the order here does not quite matter. Okay, so you can change the order. So this is definition for the z operator, z of Kasi I. Okay, so these kind of z operators should be considered as the charged fields, or at least a preliminary version of the charged fields inside the category extensions, inside the Haag-Kastler picture for charged fields. Okay, so this is about z Kasi I. So this is the first important thing we want to define. And I also want to mention that Hii fusion Hj is not just a Hilbert space. It is a bimodule. By the standard confusion theory, it is a bimodule. You can let AI acting on the left. You can let AI prime, or regular speaking, the opposite of AI prime acting on the right-hand side. So you get a bimodule. But in fact, it is not a bimodule. There's a natural way to extend it to a representation, to a real representation of the conformal net. So this is first done by Bartels, Douglas, Henriks in their paper, conformal block, about the conformal blocks. There are a series of papers of conformal blocks. Yes, I also have another different approach, which also shows how to naturally define the representation of define a representation structure of A on the confusion. But this is not quite important to my talk today. The way to define the representation A is not quite important for the purpose of my talk today. So I will just I will not say too much about this part. What I do want to say is about the locality of the charged fields. So these are charged fields, and I want to talk about the locality for the charged fields. To formulate the charged fields, let us assume that I and J are disjoint. Okay, so chart the locality is related to the associativity isomorphism. That is, suppose that you have three representations hi, hk, hj. You can first fuse hii with hk. So this is regarded as a new representation of A. Okay, and now you treat this as a whole, like the representation here. You treat this as a whole, and you let another one. You fuse this with another representation, just like you fuse this with this. Then you get this guy as a representation of A. Okay, so this is a one way to fuse three representations together. Another way is that you first fuse HK with HJJ, like the fusion here, and then you fuse this with this representation, like just like the pattern here, and then you get another way to fuse the three representations. And these three could be identified in a very natural way by identifying Kasi fusion, psi fusion eta to Kasi fusion, psi fusion eta, where Kasi is a I bounded vector of Hi, psi is any vector inside Hk, and eta is any J bounded vector inside Hj. Okay, so this is the associativity isomorphism. And after we identify these two representations of A, this is after we identify these two, so you can check that the inner product. So this is a unitary equivalence. Okay. So this, if you define the map from here to here, then this is a unitary equivalence which intertwines the actions of A. So you can identify these two not just as the same Hilbert space, but also as the same representation of the conformal net A. Okay. And after you identify these two, and we will also write these two simply like this. Okay, we will use this symbol to denote both two by removing the parentheses and simply write these two, which are identified as this guy. And now we can formulate the locality for Z, the Z operators, this preliminary version of the chart fields. You start from the first representation. You start from the first representation, HK. You use the chart fields for Kasi. Remember that Kasi is inside HII. You let this to act on the from the left of HK. Okay, this means that you let Kasi act to the left, and then you go to here. You go to HII fusion HK, because this is the left action of Kasi. And this is the right action of eta, so you are going from HK to HK fusion HJJ. But also here you can let Kasi acting on this to the left, so you let Z Kasi I go from here to here. You get this one. You let eta act to the right. You're going from here to here. Okay, so this diagram commutes. So the fact that this diagram commutes is just another way to formulate this expression. So this is nothing very new about this diagram. The commutativity of this diagram is a very obvious fact, but there is a not quite trivial fact, a fact that probably people will easily ignore, is that this diagram does not only commutes but commutes adjointly, in the sense that, okay, if you want to change the let us change the direction of the vertical direction. You take the adjoint. Okay, you take the adjoint. You take the adjoint of Z Kasi I. Then the adjoint is going from the bottom to the top, and this is also the adjoint going from the bottom to the top. Then this diagram, this new diagram, it also commutes. Okay, so this diagram also commutes, and yes, so this is a very important feature about the chart fields that I want to emphasize in my talk. Okay. I want to emphasize that this diagram is not only a commuted diagram. It not only commutes, but commutes adjointly. Okay, so this is the locality for the Z operators. Okay, so this is the first half of my talk, is to formulate the locality for these Z operators. These Z operators are the preliminary version of the chart fields in the Haag-Kastler theory for the chart fields of conformal nets. Okay. And in the second part of my talk, I want to go to the true version. So this is, as I said, this is only the preliminary versions of the chart field. This is not the true version, the version that we will finally use in the definition of category extensions. The reason that we need a better thing, we need another thing which is better than these Z operators is because when you consider these diagrams, so the point is that I want to get rid of these intervals. When we think about these diagrams, I really want to get rid of these intervals because I want to consider the objects here to be some objects inside some categories, some tensor categories, some monoidal categories. So for that reason, I just want the fusion. I do not want the intervals. I want to get rid of these intervals. So for that reason, for the reason that there are the intervals here, the reason that we cannot get rid of these intervals when we use the Z operators, it is exactly for this reason that these Z operators are not as good as we want. We want some better chart fields which go from some representations which do not involve the ij and the intervals I and j, which only involve hi, the representations hi, hj, and hk, but are independent of the intervals I and j. So this is the reason that we need to improve our story or improve our theory for the chart fields. We need to consider some better chart fields instead of these Z operators. Okay, so here is what we should do. We are going to get rid of these intervals. So here is how we do. How to get rid of these intervals? Okay, we just need to define hi fusion hj to be hi of the upper half circle called S1 plus fusion hj. So by definition, if you just write a fusion, if you do not include the intervals, then this symbol, it just means this. And this representation of conformal could be identified in a natural way with hj fusion hi is 1 minus. So in other words, this representation means that hi is sitting on the upper semicircle, and hj is corresponding to the lower semicircle. Okay, and here's one thing that you need to pay attention is that when we include the intervals, then you can freely change the order. So this guy is certainly equal to hj. I guess I made a mistake. Yeah. Sorry. So there's a mistake that I write here. So this is identified as this because you can exchange the order, but I would say this is I and j. Okay, sorry, there's a mistake here. So j is associated to the lower semicircle and I is associated to the upper semicircle, and you can identify this with this in a standard way. Okay. And also you can exchange these two orders. So this and this are the same, but hi fusion hj is not equal to hj fusion hi if you do not write any intervals here, because hi fusion hj means that hi is associated to here. But if you write hj fusion hi, then it means that hi is associated to the lower semicircle. So when you write something like this, then the left-hand side is always associated to the upper semicircle, and the second one is always associated to the lower semicircle. So for these kind of symbols, you cannot change the order of the fusion product. Okay. So next, after I define hi fusion hj, I want to relate any hii fusion hj to hi fusion hj. In other words, it is the hi of the upper semicircle as fusion hj. I want to relate this guy with this guy. Okay. Yes. This is page 8. Okay, this is page 8. And how to relate them. So to fulfill this task, what we need is how to relate. The thing we need to do is that how to relate HI fusion. In general, the question is how to relate HI and HI I1 and HI I2 fusion HJ. How to relate these two. So when the intervals are changing, then how to relate these two conformal net representations. So to consider to do this task, the first thing to notice is that when I1 and I2 are close to each other in the sense that their intersections is a non-empty connected open interval. So this is a picture where I1 is close to I2. These two are pictures where I1 is not close to I2. So when I1 and I2 look kind of like this, then you can define an equivalence of the representations of the conformal net by just identifying Cassey fusion eta with Cassey fusion eta, where Cassey is any vector inside Hi of I1 intersect I2. So the point here is that Hi of I1 intersect I2 fusion Hj. So the vectors inside here, the vectors generating this Hilbert space is dense inside here and also dense inside here. The vector inside here is dense inside here and also dense inside here. So this could be identified with this, and this can also be identified with this. So when I1 and I2 are close, you can identify these two Hilbert spaces. In fact, this is not an equivalence of Hilbert spaces. This is an equivalence of the conformal net representations. So you can identify these two using this formula by identify Cassey fusion eta with Cassey fusion eta, where eta is any vector inside Hj and Cassey is any vector inside Hi of I1 intersect I2. Okay, so this is a very important observation. I believe this is not a difficult observation, but it is a very important observation. It allows us to change the intervals. It allows us to unitarily relate the confusion for different intervals. Okay, and now I can tell you how to relate HII fusion Hj with Hi S1 plus with Hj. Okay, there are actually a lot of ways to do this kind of relation. For example, your I is here, your alpha semicircle is here. Okay, you can first go from here to here, because this interval is close to this interval, because this intersect with this is a non-empty connecting open interval. So this is close with this, and this interval is close with this. So from here to here, you get an isomorphism. From here to here, you get an isomorphism. You take the composition, you get an isomorphism of representation from here to here. This is one way. Another way is going in another direction. From here to here, this is close to this, this is close to this. So from here to here to here, you get another, and then you take the composition, you get another isomorphism from this representation to this representation. And you can choose some more complicated paths. You can start from here, and then this interval is close to this, this interval is close to this, this interval is close to this, this is close to this, this is close to this, this is close to this, and then you combine all of them together, you get an isomorphism from here to here. Okay, you can think of this isomorphism to be an isomorphism which is induced by the path. Okay, so we have different paths, and different paths will give you possibly different isomorphisms. So this is something. So different paths will give you different isomorphisms. So these might not be the same. These isomorphisms, all of them are isomorphisms from here to here, but they might not be the same. Okay, different paths will induce different isomorphisms of the conformal net representations. Okay, so let me summarize what we have now. We have isomorphism from Hij to His1 plus fusion hj. Recall that this is just the standard fusion hi box tensor hj, and we have a lot of isomorphisms, right? And we need to choose. We just need one isomorphism. So how to choose the one isomorphism? It's impossible. If you just think about the interval I, then it's impossible to choose a standard isomorphism from here to here. So to choose a standard isomorphism from here to here, we need to consider not only the interval, but its branch inside the universal cover. In other words, we need to consider the argument function of I. Okay, so I together with its argument function is written as I tilde. So we need to consider I tilde, but not just I. And you can consider I tilde as a branch of I inside the universal cover of the unit circle. So arc I is a continuous function, continuous arc function of I. Okay. And once you choose an argument function, once you choose a branch I tilde, then there is a standard way to choose a path, choose an isomorphism from here to here. Let me tell you how to choose the isomorphism. To choose the isomorphism, we need to choose a path. Okay, how to choose a path? We define the path, which is called alpha I tilde, from I to the upper semicircle in such a way that the argument of I is changing continuously to the standard argument of the upper semicircle, which is from 0 to pi. For example, look at this. You take the I to be here, and I tilde is I with an argument. Suppose you choose the argument from 3 pi over 2 to 7 pi over 4, then to change continuously to 0 to 2 pi, 0 to pi, you just need to go like this, here, here, here. By going in this path, this argument is changing continuously to this argument associated to the upper semicircle. If you choose the argument of this interval to be negative half pi to negative 1 over 4 pi, then to change continuously to 0 to pi, you need to go in this direction. It is changing from a small negative number to a small positive number, which is from this to 0 to pi. So you should choose this path. You should choose the path here. If you choose the argument of this interval to be this, then you should choose a more complicated path. If you choose to be this, then it is even more complicated. Okay, so these are some examples that for the same I, if you choose different arguments, if you choose different branch of the I inside the universal cover, then you will get different paths. But these paths are uniquely determined by I tilde. It is not uniquely determined by I, but these paths are uniquely determined by I tilde. And you can use this path to choose a standard isomorphism from HI fusion HJ to HI fusion HJ. Okay. It is called alpha I tilde with bullet. Okay. Alpha bullet of I tilde. So this is the isomorphism induced by the path that I choose here. Okay, to summarize, if you consider I tilde, then you have a unique choice of the path, and then this unique choice of path give you a unique choice of the isomorphism. Okay, so this tells us how to relate the interval associated to the interval I with the standard interval, the upper semicircle. This tells you how to relate this fusion with this fusion. And for the similar reason, you can choose to not go to the 0 to pi. You can choose to not go to the upper semicircle, but go to the lower semicircle. We let beta j tilde to be the path, the unique path from j tilde to the lower semicircle, such that the argument of j is changing continuously to negative pi to 0. So if your j is here, the path could be here, could be this, depending on which argument you choose. And similarly, j tilde determines a unique path from j tilde, from j to s1 minus to negative pi 0. And then this path gives you an isomorphism from hi fusion hjj to hi fusion hj of s1 minus. So recall that this is also hi fusion hj. Okay, so this is another way to relate the general confusion with the standard confusion. I would call this kind of to be the standard confusion. I will call this kind of confusion to be the general confusion. Okay, we have the paths to relate the general confusion to the standard confusion. The choice of these paths are determined not only by the interval, but also by the argument of the interval. Okay, and now we are ready to define the true charge fields. So the Z operators we defined previously are just some preliminary versions. The L operators and R operators that I'm now going to define are the real charge field operators that appears in the definition of the categorical extension. So suppose that C is I bounded and eta is J bounded and HK is another representation. Then you can define L of C and I tilde to be this. You let Z of Ci going from HK to this to HII fusion HK. And you let the isomorphism you choose to go from here to here. And similarly, so this is considered as the right action. This is considered as the right charge fields. The left charge fields. The right charge fields is that, okay, you first let Z of eta j go from HK to HK fusion HJJ, and then you let beta J tilde dot go from this to this. It comes from here. So L is, you can regard L as acting on the left. You can regard R as acting on the right. So this is a left charge field. This is a right charge field. Okay, so these are the left operators and the right operators. And let me tell you how to formulate the locality axiom for the L operators and the R operators. To formulate the locality, we need to require not only that the interval I is disjoint from the interval J. We need to require something more. We need to require that J tilde is clockwise to I tilde. It means this. It means not only that I is disjoint from J, it means also that the argument of J is an argument of I satisfies this relation. For example, this is an example of J tilde clockwise to I tilde. So it means that the argument of J is smaller than the argument of I, but not very much smaller than the argument of I. So this is an example where J tilde is clockwise to I tilde. The argument of J is slightly smaller than the argument of I. In this example, the argument of J is greater than the argument of I. So we do not say J is clockwise to I. Instead, we say that I is clockwise to J. In this picture, J is also not clockwise to I because the argument of J is too much smaller than the argument of I. So we only say this kind of arguments relation to be the clockwise relation. Okay, so this is the meaning of saying J tilde is clockwise to I tilde. Okay, and after saying what is the meaning of clockwise, I can tell you how to formulate the locality for the L operators and R operators. So the locality axiom is the most important axiom in the definition of the categorical extension of conformal net. It says this: you choose representations, you choose representations HK, HI, and HJ, and you choose intervals I and J, and you choose I tilde and J tilde, which means that you do not only choose intervals, you also choose their arguments. And we require that J tilde is clockwise to I tilde, which means that not only is I disjoint from J, but also it should look like this. Okay, so this is our requirement on I tilde and j tilde. And let's choose C to be inside HII and eta to be inside HJJ. And then you can let L, the L operator, L of C I tilde. Recall that it depends not only on C, but also on I tilde. Okay, so this operator depends on C and I tilde. We let this operator act from the left of HK. Okay, it is acting to the left of HK, so it goes from HK to HI fusion HK. This time, there are no intervals inside the confusion. All the confusions are the standard confusions. In this picture, we are totally getting rid of the intervals. The intervals only appear inside the operators, the chart fields, but do not appear in the Hilbert spaces. Okay, so this is the good thing. This is the good part. Okay, so L is going from HK to HI fusion HK, and the R operator is acting on the right. It is going from HK to HK fusion HJ. And similarly, you can let L of C I tilde act to the left of this. So you let HI fusion this guy, you get this. Or you can let R act to the right of this guy, you get this. Okay. So we have this diagram, and the locality axiom says that this diagram commutes adjointly. Okay. It commutes adjointly, which means that not only does this diagram commute, but also if you flip the horizontal direction, if you replace this by its adjoint, the vertical arrows are going from the bottom to the top, then the new diagram is also commuting. Okay, so this is what we mean by saying that this diagram is commuting adjointly. Okay, so this is the formulation for the locality axiom inside the category extension. Okay, so the last page, I have one more page, so I think I have time to mention one last thing of my talk is another axiom called the Braiding Axiom. The Braiding Axiom tells you how to relate the left operator with the right operator. So think about this. Think about the path changing continuously from the upper semicircle to the lower semicircle. You think about the path here. It is going from the argument 0 to pi to the argument negative pi to 0. You consider this path. And this path induces a isomorphism of conformal net representation. It goes from HI of S1 plus fusion HK to HI of S1 minus fusion HK. So because this on the left-hand side, HI is associated to the upper semicircle. So when you get rid of this interval, it is on the left. On the right-hand side, because HI is associated to the lower semicircle, so if you get rid of this interval, it should be written on the right. Okay, recall that when you write the standard confusion, when you get rid of the intervals, then the left-hand side is always associated to the upper semicircle, and the right-hand side is always associated to the lower semicircle. So this path induces an isomorphism from HI fusion HK to HK fusion HI. This isomorphism is the Braid isomorphism. Okay, and the Braid axiom says that there is an isomorphism of conformal net representation, which is unitary and makes this to commute. And because this is unitary, this diagram also commutes adjointly. Okay, so this is the Braid axiom. Roughly speaking, it says that there is a Braid operator which relates the left operator and the right operator by this commuting diagram. Okay, this is the Braiding axiom inside the category extension. And actually in the formulation of Braiding axiom, we do not require these braid operators to satisfy the hexagon axioms. The hexagon axioms are indeed a theorem. It could be implied by the other axioms of the category extensions. It is not something we require. Okay, so this is one feature of the category extensions. So let me close my talk by saying that the category extensions is just a list. The definition of category extension is just a list of axioms satisfied by the L operators and R operators. And in this talk, I tell you two axioms, the locality axiom and the braid axioms. Okay, so I think I should stop here. Okay, thank you very much.